ask for the people who would like to discuss during the night that they should move in this part during the night. And during the night means about 11 o'clock or about that time. So this is for yesterday evening. Then the second remark, I would kindly ask you, even if you don't have any time, because you have so many interesting talks together in small groups, that you take your time to be here in time for the lectures and the workshops. Then the last two students arrived yesterday night because they had in mind that they had to arrive yesterday, that we would start today. So the last student came at 11 o'clock in the evening. So now I think everybody is here who planned to be here. So welcome for these two students. Then we start today with the next two lectures, and I would kindly ask the student who is presenting, Ramis. You are doing that?
Yep.
Yeah.
You can give the talk if you like.
Good morning, everyone. As we have mentioned that we were late night here and making a lot of noise, and we came late today. So the penalty is that Ramis exactly wants 1 hour, so it will be extended. So we will be at least 6 minutes later. Yeah, so that's the penalty. I would like to introduce Dr. Ramis Movassagh. He will be our speaker today, and he will be talking about idea of time in physics. I would like to give a short introduction about him. He did his bachelor's in applied and engineering mathematics from Cornell, after which he did his pre-doc at ETH Zurich, and he finished his PhD in mathematics from MIT. Outside his academic life, he likes to do martial arts, and he likes to be active, so he's also running, and he also likes to read a lot. I would not take, and yeah, most importantly, yesterday after the speakers panel, I had a talk with him outside, and he really thinks that we can travel back in the time. So I think it will be very interesting to listen to him, and I won't take much time, and I would like to ask Mr. Dr. Ramis Movassagh to take a stage.
Thank you, thank you. Okay. So, time is limited, so let me ask you a question, and please answer fast because I got a lot of material. What is time to you? Anybody? If some alien came and had no conception of time and asked you what is time, what would you say? Change. Tick-tock is nice, so the clock. What clock measures?
Progress.
Progress, all right. So, you know, it's difficult to say, right? So I looked up on Oxford Dictionary. It says the indefinite continued progress of existence and events in the past, present, and the future, regarded as a whole. So that's what the dictionary would tell you, right? That's where you would look. Then you look on the Wikipedia, of course, and it says time is the continuing sequence of events occurring in apparently irreversible succession. Ooh. Okay, guys, so we're not going to finish the talk. But it'll be slower. So, it's the continuing sequence of events occurring in apparently irreversible succession from the past through the present to the future, and measure of duration and frequencies of events and intervals. So notice these underlined stuff. So you have indefinite continued existence, past, present, and future. So I want to tell you how, you know, physics will tell you that none of these are really accurate. So the dictionary definition is by no means accurate. So let's get into it. So, like you said, less controversial definitions are that time is what clocks measure. Somebody was being funny. Time is what keeps everything from happening at once. Time, you know, there's two ways of looking at it. One is, what does physics say about time? The other thing is, what does time mean to physics? Right? So time is very important in physics because we have experiment. Something is scientific when we can experiment and verify it. So for example, if I find some kind of a superconductor with some properties, I can tell Reinhard about it. He goes back 2 weeks later, he makes the same measurement, he finds the same property, he tells his friends, they make the measurement, they find the same property, then we have something. Okay? But the underlying assumption is that regardless of when we do the experiment, I do it now, he does it 2 weeks later, somebody else does it a month later, we expect to get the same thing. We never say that, okay, he could not get the superconductor because he did it 2 weeks later. Okay? So this homogeneity in time is underlying the experimental verifications that we do every day. So the scientific method relies on homogeneity in time, and the scientific arrogance is that we scientists believe we can understand, right? We think that it's in principle possible for us to understand nature. And interestingly enough, so if you read Stephen Hawking's book, he has a quotation that says, the eventual goal of science is to provide a single theory that describes the whole universe. Okay? And interestingly enough, if you look at this unification, it started with Newton, really, who came and said, apple falling on the floor and moon going around the earth are really the same thing because of the same gravitational force. And after that, things kept going, right? People kept trying to unify. Maxwell came and unified electricity and magnetism. Einstein unified electricity and magnetism and mechanics. And this trend kept going on. And interestingly enough, when you look, people, this believing system that you can reduce everything to a single point grew and flourished in countries that had monotheistic religions. So interestingly enough, in West, people tried to somehow reduce and reduce reductionism to a single point where everything starts from a single equation, the equation of God and these things that you see and hear, is interestingly enough ingrained in the minds of Westerns, I believe, more than the Easterns. I mean, we didn't have any such ideas in China or in India. There were some particle physicists in Japan, but mostly it was in the West. Perhaps it has some connection. Okay, so what is physics, right? I'm going to tell you about time in physics. So physics, if anything, is concerned with, we have particles and interactions. And the goal of physics is you tell me where the particles are, how they're moving at a given time, how they're interacting with each other. Then a good physical theory would tell you how they will evolve in time. So you give me the initial conditions, what the particles are and their interactions. Me, if I were a good scientist with a good enough computer, I would tell you how it would look on sometime later, right? Be able to predict the future of these things. Now I want to tell you why physics is different from mathematics. This is the well-known equation, F equals ma, right? Newton's second law. Everybody has seen this. And this part, you thought you were going to get away without seeing an equation. Physics does. That's right. Well, not quite. This is the second time derivative. So this is twice the derivative of x with respect to time. That's what acceleration is. You see, this part is mathematics. If you knew what this was equal to, you could just integrate, okay? Equations of motion and get x as a function of t. But what it's equal to is where the physics comes in. This is empirical. That F, force between particles, is a function of distance. And that you have to go measure to know what the gravitational force is. You can't just make it up out of mathematics. Nature will tell you that. So that's where the physics comes in, okay? And then you can integrate and, hopefully you can integrate with a good enough computer and tell what the future will be. Now, can you really do that, right? Is it really possible to integrate the equations of motion and deterministically tell what's going to happen in the future? So a Persian philosopher, scientist, astronomer, wine drinker, Omar Khayyam, in a good day he probably could do a lot more. He's really started this determinism, the idea of determinism. He was the one who basically said, and he was a poet too, and the first morning of creation wrote what the last dawn of reckoning shall read. Which means, God created the universe, closed all the degrees of freedom, and you can integrate to infinity. Okay? That's what he really means. So it's fully deterministic. Now, quantum theory seriously challenges this, but this idea goes to this idea of so-called block universe. I didn't know it had a name. I called it static existence, but apparently people have been calling this block universe. So throughout this talk, I will not be able to, the physics as we know it is 4-dimensional, 3 spatial dimension and 1 time. But I can't draw 4 dimensions. So I'll do 3 dimensions, okay? As if the world is 2-dimensional. There's X and Y and there's time. The truth is that there's another Z, but, okay? So, it's impossible. So block universe idea is that all of us, existence as a whole is there, all right? Space and time as one entity are there. The reason we see things different is because we explore it, ephemeral lives differently. So somebody starts at this spatial point, someone here, And they have some life events and some life trajectory that just differs from the other. Sometimes they cross each other, sometimes they don't. But it's there. It's just how we explore it, and our conscious mind draws a distinction between our different lives and thinks the existence is somehow dynamic. But the truth is that it's just there, okay? Well, quantum theory really challenges this idea, but I just thought I should tell you about it. So, and Newton, probably the tallest figure in theoretical physics, he thought time was absolute, determinism was, so he pushed the ideas of mechanics and determinism to as far as, we had him till Einstein. He thought time is absolute, true, and mathematical, and it flows equably in both directions. So nobody really knew what the hell he meant by equably, and it turns out that what he really means, I think, and I think it's not new, everybody knows this. So F equals ma that I told you about, you can integrate it forward in time, you can also integrate it backward in time, right? And if you integrate it forward in time, you make predictions. You integrate it backward in time, you verify history. Then you can tell the good historians from bad historians, because so at a given moment, you can, in principle, predict the future and the past, because you can integrate in either direction. That's what he means by equably. Okay. Okay. So now the arrow of time. Up to here was, it's okay. So up to here was just mechanics, point-particle interactions. Now I want to tell you about irreversibility we see in nature. So if I showed you two pictures, one, I told you I've taken a picture of an egg. One on top of a tabletop, the other one smashed on the floor. Which one do you think happened after? Thank you. So the smashed one will be the one that you would think has happened. So I give references all along. If I forget to say them, you can look at Sean Carroll's book, Schrödinger, What is Life? Who Prize for a Philosophical Discussion. So, okay, so this is, the arrow of time is the perceived notion that past, present, and future are different, okay? We feel that if somebody plays a movie forward and somebody plays it backwards, we can tell which one is forwards and which one is backwards, right? We know that an egg can break and it cannot just spontaneously come together and make one nice shell. This is the arrow of time. Now, let's use the workhorse of statistical physics, ideal gas. So if I start with gas molecules in one corner of the room. Suppose the whole air, I just smash them in one corner. And gas molecules are like energetic ping pong balls. They want to run around in some temperature. And would you believe that sometime later it would look like this? Right? It would fill the room. But the question is this possible? If I start with the gas molecules here, can they at some time later all go in one corner? Not possible? Okay, it's possible, right? So, like you said, Boltzmann said the same thing. He said it's possible, but you would have to wait a long time, right? Right? You wait a long time, and hopefully, at some point, all of them come together in some weird configuration with a low probability fluctuation. They all end up in that corner at one moment, and then they go back to this macro state, okay? So this particular configuration we call a micro state with an I, micro state, okay? So this is a micro state, this is a micro state. A set of macroscopically indistinguishable microstate is called a macro state. Now, what does that mean? So here, if I interchange these molecules, it'll look the same. It has the same pressure, temperature, and so forth, okay? So this macro state corresponds to many, many possible ways of arranging these atoms or molecules in the room, and it'll be the same macro state. It'll have the same thermodynamical properties. But this particular micro state, I could exchange them a little bit, but you see, I have to be confined to this area. So the set of microstates corresponding to this particular configuration are a lot less, okay? So if you think of D as a disorder, so it's the number of ways, it's the lack of information, it's the number of ways you can arrange these molecules to get the same macro state. So if you forget about the information of the arrangement, how much can you infer? That's the amount of disorder. So, here, there are many possibilities. There are many chaotic initial conditions that would have this as the same macro state, same temperature, pressure, and so forth, and not many here. So the amount of disorder here is a lot more than here. Another way to look at it is to specify this as a macro state. You don't need much information. You say it has some temperature, pressure, and it'll be done. You don't really care about where things are. But to specify this, you'll have to say a lot more. You're like, it's there, it's not everywhere else, They're in this one corner, they're moving this particular time at that direction, and that's why they ended up there, okay? So this disorder is so entropy is proportional to the logarithm of disorder, and log grows like this. So entropy is an increasing function with disorder. And so entropy is the lack of information. If something looks very boring, homogeneous, and everywhere you look, it looks the same, it has a high entropy. If it's got structure, like us here, right? If I wanted to describe this room, I would have to provide a lot of information. So us, compared to an ideal gas, we have much lower entropy, okay? So there's more information content. Now, this second law I told you about, so this gas that we just saw, these are the set of microstates that correspond to that particular macrostate that looked very particular, okay? As time evolves, this phase, suppose this point identifies the whole configuration. This is a point in the phase space. This will evolve very fast into that homogeneous state, and these are all the set of microstates that correspond to that homogeneous state you just saw. Now, this picture is a little misleading because in truth of the matter, this is so overwhelmingly smaller than this. So very fast, you go from these low probability states to these maximum probability states. And that's the law of increase of entropy. We say entropy never decreases. So the reason we see irreversibility in nature is because probabilities flow that way. The probability of things happening in one particular direction are overwhelmingly higher than the opposite direction. So an egg that falls on the floor, in principle, it hits the floor, there are these sound waves that get into the floor, jiggle the atoms, they get dissipated into heat. But in principle, this heat could reorganize, come back into sound waves, go underneath, kick the egg, and the egg goes up. All these atoms arrange themselves in some particular way, very special case, and just come right on top of the table like before. Okay? Now, that doesn't happen because probability is extremely low, but it's not against the laws of physics. It could happen if you just designed it so. Now, if you wanted to, so in a closed system, entropy always increases. If you want to do that, kind of induce it without waiting a really long time, then you would have to come in from outside and put in work, and then make things happen, glue the shell together and so on and so forth, okay? So in a closed system, things flow in this irreversible way we saw. There's this arrow of time, all right? Now, equilibrium, this homogeneous state, is death for living systems. And so the question you ask is, well, I just told you entropy is always increasing. That's just probability, that's just logic. If entropy is always increasing, then why do we have complexity in the world? Why do we have life? Why do we have so much structure? Why do we have galaxies, plants, ecosystems, living matter? So I told you that entropy is log of disorder, D is the amount of disorder. The way living systems do this is that they draw order from universe. They draw order from their surrounding. So what is order? Order could be thought of as 1 over disorder. More disorder, lower order. You make disorder smaller, order grows, right? So forget S drawn for now, 1 over D would be amount of order. You could think of it, some functional form. And log of 1 over D is minus log of D. It's just a mathematical thing. It's a fact of mathematics that logarithm of 1 over anything is minus logarithm of that thing. Okay, it just is the fact. That's true. So just take my word for it for now. Log of 1 over x is minus log of x. Okay, or log of 1 over d is minus log of d. So the entropy you draw is by drawing order or 1 over disorder from the living systems. Now let me put it in a pictorial form. So we eat, right? This is one way of staying alive, gives us energy. And you have celery, you have fruit. You see, there's so much information you need to provide to say the state of this fruit, right? It's not some kind of uniform. You can't say it's just some, blue mess, right? It's not. And we run around. So I'm not going to put words into this, but this is the final state of the food, right? You start with this, you eat this, and this is what it ends up being. And this is very low entropy, okay? You provide the color and the temperature is done, right? This is very low entropy. And here, when you run, you radiate. And radiation is the highest disorder possible state of matter. Radiation is very disordered. It's worse than gas. It's like a gas, but with photons, okay? So also radiation, running and exercise can keep you alive longer because you can push entropy back and not give in to the second law of thermodynamics. So living systems stay alive because they push equilibrium back and they kick around longer than they're supposed to. So now the question is, why does the universe find itself in a state where we can't even fight entropy? Why aren't we at a state where everything is so uniform that, we don't even have structure to begin with to draw order from it? So, nobody knows, but Boltzmann probably said it right if you make adjustments, but the philosophy is right. He said that in nature, the transition from a probable to an improbable state does not happen equally often as opposite transition. So if it did happen, we would be at equilibrium. Okay? If it doesn't happen, it means we are not at equilibrium. Should be sufficiently explained by the assumption of a very improbable probable state of the whole universe surrounding us. So he thinks the universe that we are in is not this very maximum probability state. It's some very low probability state. It just happens to be the case. We don't know why. And that's why life can emerge. And soon we're going to go to this equilibrium state. So he thought our lives is just some kind of a rare fluctuation on this eternal, existence of nothingness. Now, so that idea philosophically may be on the right track, but with the current understanding of cosmology, things are a little different. Okay. So we believe now that the world started from a Big Bang. You see, Big Bang was very simple. So there was a big ball of plasma. Some few seconds after the Big Bang, homogeneous plasma, tremendous amount of light, energetic light. And the description is very simple, right? Then later, some little time later, 10 to 10 years later, we have a universe that's bigger, and it has a lot of structure. You have atoms, galaxies, goats, and Mitt Romney. And the description is complex, right? If I want to describe this world, I got to provide a lot of information to tell you what it is. So it's complex. Complexity, entropy always increases, but here it's more complex. Now, if you wait a little longer, it turns out that most galaxies have a black hole in the middle, and black holes are sucking matter like there is no tomorrow, and they have very high entropy. So long time later, 10 to 15 years, the world is going to be possibly a single black hole. Okay, everything has been swallowed in, or maybe there are a few black holes, and they'll coalesce later. And this is, to be artistic, this is the last planet falling into the black hole. It's the end of, this is the doomsday. And black holes, according to Hawking's theory, they radiate. But you see, before I go to the next step, you see entropy is again higher, but it's simpler now. There are no goats, there are no Mitt Romney, there's only one big black hole, right? And this black hole radiates. Now, black holes dissipate, they kind of die by radiating, so the ultimate state that will be the case for infinity will be this gigantic universe with just photons, radiation, the maximum disorder possible. This black hole has evaporated all the way, and there's nothing there, and it's going to be like this forever. Okay, so it seems like entropy always increases, but complexity first increases, then decreases, and it's in this region that life and all these things that we see around us are possible. We don't know exactly where the center is, but this existence of complexity is the reason we can have a life. Now, what's the source of that complexity? It could be a fluctuation, like Boltzmann said. It's not so clear yet. Okay. So actually, this is where the talk is supposed to start. So I'm going to tell you about the 20th century, so quantum theory and Einstein's relativity. Einstein's relativity is causal, is deterministic, whereas the quantum theory is probabilistic. We have the Heisenberg uncertainty principle, and it has various features that are at odds with relativity. You put them together, just a special relativity and quantum mechanics, you get quantum theory of fields, and they all have profound consequences that I want to tell you about, if I get the chance to finish the talk, okay? I'll try. How am I doing on time? How am I? 30 minutes. Okay, just 30, okay. So, Einstein's relativity, these are good references, Weinberg, Rindler. So, Newton came and said space-time are absolute, and his equations implied that the equations of motion were relative. He insisted that time and space were absolute because he was very religious. He thought God is absolute. Therefore, his space and time must be absolute. He was severely criticized for it, but he held on to the belief that space-time were absolute. And Albert Einstein came, and he said, well, absolute equal mathematical time, my space-time, further, he said, is not absolute, it's relative. Well, it's a big misconception. I think everybody think he said it's relative. What he really said was it's relative. All right? And so this is my contribution to the history of science. So he was fascinated by Maxwell's theory that unified electricity and magnetism. And in Maxwell's theory, a byproduct is that speed of light is a constant. So at the time, everybody was so mesmerized by Newton that they said, well, we have to kind of justify why light comes out as constant. Maybe something is wrong with Maxwell. Maybe, we have to have an ether that justifies everything. And Einstein was, ignored. He had been isolated. The community didn't want him. He was bright. He knew he was bright. So he was both detached and hungry. So he went and worked really hard and hammered out the consequences of, and his original thought, the odyssey, was that he, instead of trying to massage the speed of light into the past framework, he said, I'm going to use the speed of light as the starting point and see how physics has to reorganize to give in to the constancy of speed of light. So we have all these ideas in physics, see how they have to reorganize themselves if the true concept that they had to hold on to was the constancy of speed of light. And by doing so, he unified mechanics with electromagnetism. It's a very, very simple theory, but like most good theories, many things come out of it. For example, you get that energy equals mc squared, equals mc squared. And apparently in the army, you have to say m equals e over c squared to show that energy and mass are equivalent. So with this, the whole conception of mechanics changed, and when you apply that to gravitational fields and gravitational masses, you have a new cosmology. Because then the Newton's laws are not what telling you about the universe. You have constancy of speed of light and Einstein's relativity. So Einstein fell into the same pitfall that he had avoided earlier on. His equations showed that the universe was dynamic. It had to contract, it had to expand, he had to do something. It was not static. So he, instead of accepting it, tried to justify it by introducing fudge factors to make it static and things like that. But it took, this very happy Russian physicist, Friedman, to come along. He took Einstein's equations at the face value and solved them and got 3 types of universes. He actually got 1, but now we know that if he had done it correctly, there would be 3. So one solution is that the universe expands, and then there's gravity, right? Gravity is pulling in. It expands, stops, and contracts and crunches, okay? So from the Big Bang, you expand, then you slow, stop, and come back. The other one is that expansion is so fast, that the gravity has no hope of stopping it. It's just going to expand forever, okay? The other one is that it's just in between. It expands, slows, but only stops at infinity. So practically it'll never stop, but it'll stop at infinity, okay? So which one of these is it? If we solve Einstein's equations, you see all of these will slow down the universe. Some of them will just never stop it, but gravity always slows down a little bit. So which one of these universes is it if we solve Einstein's equations? It turns out that it's none of them. Now we know that the universe is expanding and it's accelerating as it's expanding. We have the so-called dark energy. So it's a real mystery now. Why, right? So that Einstein fudge factor that he introduced to make universe static, had he just left it and chilled out, now it would make sense because that fudge factor would make it accelerate, right? Before it was contracting, he put it in to make it static, but now we know that it's expanding, and if you had it in there, it would be accelerating because, anyways, it would be the same energy. But regardless of what the solutions are, there's one common feature in all Einstein equations. They all have a beginning. 13.7 billion years ago, if you solve them backwards in time, you see that the distance between all matter should have been 0. That's the so-called Big Bang, okay? And, that's where apparently space and time start. Now, time travel. So if you look at Einstein's equations, there are many possibilities. One is time travel. Like we discussed yesterday, going into the future is easy. You just wait. But you can also fast forward into the future. So if you're here, I get on a rocket ship, and I move really, really fast away from you, close to the speed of light, and I come back. I could, in principle, come back a week later, my time, and I come back and the Earth is not here anymore. It's how much the ticking of my clock is different from your clock, because I'm moving fast and I come back, that acceleration. But the question is, can you move into the past? Now, moving into the future is fine. You see, there are no paradoxes. But moving into the past has logical issues, because you can't go and influence the past. Then who were you that went into the past? Like we discussed, you can't go shoot your own grandfather, and if you do that, then who was it that traveled in the future? So it's paradoxical. So this is Kurt Gödel. before I tell you about his work, I want to ask you a question. If you look at this picture, forget about the name, what can you tell about him? He was arguably the greatest logician of all times, and it has its goodies that are attached to it. He was a very difficult patient. So when he went to the doctor, he would argue with the doctor for hours about what is really wrong with him. So the doctor is like, then why did you come here? So he, at the same time, didn't have the courage to treat himself, but he wanted to convince the doctor so he would be fine with the prescription he thought was right for him. So he came up with the incompleteness theorem, which is like the uncertainty principle for mathematics. It says within a set of axioms in mathematics, you can have theorems that you cannot prove or disprove. So even in something as clear-cut as mathematics, you can have theorems that you just cannot prove or disprove. It's not a question of how good you are. They just cannot be proved or disproved. And apparently when, during the Second World War, he came to the US and took the US citizenship oath. He raised his hand. The judge is like, yeah, what's up? He's like, I read the Constitution and I found an inconsistency in the American Constitution. He was a good friend of Albert Einstein, really admired Albert Einstein. So he looked at Einstein equations and he found a solution in Einstein's equation that disturbed both of them. And I want to read it to you. So this is the paper, 1949, Reviews of Modern Physics. And if you read here from IE, it is theoretically possible in these worlds, he means in his solutions, to travel into the past or influence the past otherwise, or otherwise influence the past. So his solution allows for time travel. Now, if you read his life, Kurt Gödel died because if you read, they say he was mentally unstable, he refused to eat, he was paranoid that he was going to get poisoned, and his wife got hospitalized for 6 months. The only food he ate was his wife's cooking, nothing else. And when the wife got hospitalized, he eventually starved to death. Okay? Now, this is what you hear, but I've heard from other people who knew him directly or maybe a little indirectly, what was really going on in his mind, now this is just a conjecture, was that he thought people from the future would want to come back and get rid of him. Because he found this solution to the Einstein equation. And through his thought, he thought, they would be chemically so advanced that they would want to do it through food. And he had thought about it, and he thought the most probable way of surviving would be to eat his wife's cooking only. Okay? And yes. So his solution has some features that the whole universe has to be rotating. And the mathematical side effect is that you can travel into space-time, come back, and your universe has rotated under your feet, you come back to a different space-time point. The good news is that we know there's no such Gödel rotation. If you look at the universe now, there's no such a thing. Okay? It was a mathematical possibility, but physics doesn't allow it. And it doesn't have expansion. And so the model is just, good mathematical toy model, but, it doesn't work. The bad news is that there are other ways of time traveling. So you could go, for example, faster than the speed of light, but that is, if somebody tries to sell you a theory that, in it, at some point you have to go faster than the speed of light, ask them if they sell used cars for a living. So we cannot go faster than the speed of light in general theory of relativity, but what you can do is you can curb space and time so much. Let me show you another two-dimensional. This was the so-called cosmological bridges, what we call wormholes now, were actually discovered by Einstein and Rosen in 1935, the same year that Podolsky joined them and they made the entanglement prediction. The idea is that, so this is a section of the universe. By the way, I don't know if I mentioned this. So when I talk about finite universe, things may be finite, but there are no boundaries. Did I say this? So like the surface of the Earth is very finite, but it doesn't have a boundary. You go and you come back to yourself. Any closed surface has this feature. Okay. Yeah. So here I've cut a section of it. There's no falling. There's no cliff that you fall in this space-time. Okay. But the two-dimensional version is like a surface of the Earth, but there's a four-dimensional analogy where it's closed. It could be finite, but it's like a surface that closes back on itself. And that's how space-time is. So a wormhole, you see, normally if you want to travel from this point to this point, you would have to go like this, okay? But you can put a mass here, like a black hole, and another black hole here, and they curve space-time so much that you can tunnel through. If you get here, you just go right down. And, it's a very different, it's much faster, could be, that you can really tunnel through gigantic space-time distances, cosmological distances, by curving the space so much and having them in some controlled way. So that's what a time travel machine would do, would take you to this point and get you across. So there are some technical difficulties, but in principle, it's possible. So I want to tell you about the quantum fabric of space-time now. So that was relativity. The quantum mechanics has uncertainty principle in it. So quantum mechanics is inherently probabilistic. The best you can do in prediction is to calculate probabilities of things happening. You can never say with certainty what exactly would happen. But the best you can do is to say what is the probability of something happening, to calculate the probabilities. So to join them, E equals mc squared from relativity, because I'm talking about quantum field theory, which is the marriage of relativity and quantum mechanics. And this is the uncertainty relation, which says if you want to understand small time scales, then you have to provide a lot of energy. The uncertainty in energy and time and space and momentum have a bound. So if you want to understand small scales, you have to provide a lot of energy and momentum. And that's why we have accelerators like CERN. You have these gigantic energies because you want to understand particles at very small scales. And you need those energies to be able to probe them at small scales. That's just uncertainty principle. So then the question is, what is the fabric? I mean, I told you the cosmological origin, but if I start with a piece of vacuum, I mean, there is nothing more boring than vacuum, right? By definition is emptiness, right? It's as boring as it gets. It turns out that if you look into the vacuum, suppose you want to understand vacuum, as boring as it is, what kind of material property does it have? If you look into it, you see if you get close to it, the amount of energy you have to provide will allow for creation of particles, because E equals mc squared. The energies you have to put in will allow for a pair production of, say, electron and positron. And I drew them in this particular way because there are some conservation laws that have to be obeyed. Like charge has to be locally zero because vacuum was zero, and there's some angular momentum and momentum that have to sum up to zero. So in short time scales, the vacuum can have particles created and annihilated. So when you look closely in the vacuum, it's far from boring. Actually, it's too exciting. If you look into it, there are all these particles that come into life very short, and they just die very short. So it's like a soup of boiling particles that just are sparkling, right? And again, this is going this way, this is going that way because of some conservation laws. So it scales of 10 to the minus 13 and minus 16. This is how the vacuum really looks like. It's far from empty. But this description, all the way, physics all the way, so we started from cosmological scales, which were very big, now we're going the other way. So the scales 10 to the minus 16, everything around us, almost everything around us is fantastically explained by the so-called standard theory, standard model in particle physics. So electromagnetism, which is most of the phenomena around us, particle physics, they're all part of this grand theory we have, this standard model. And when people talk about going beyond standard model, they're talking about even shorter time scales. But there is, as far as we know, no failure of standard model at the time scales, space-time scales bigger than 10 to the minus 16. Okay? So now we have the little Higgs apparently, which is a real confirmation that the standard model was the right way of thinking about it. The little Higgs were these particles that they were trying to find in CERN, and they did. It seems like they did. And some of the experiments have been verified to a part to 10 to the 11. 10 to the 11 is 1 0 with 1 1 and 11 zeros. So the amount of error is extremely small, right? Now, to show you one of these experiments, which is my favorite, you see, here, suppose an electron is sitting here in the vacuum, and I want to measure its charge. From a distance, it has this constant charge of an electron. But when you get close to it, if this is what's happening around it, these have polarities. They can, you see, this has some charge. So in principle, you could think of it as a dipole. So the vacuum can polarize and shield that charge. Because of all these particles in it, the vacuum can polarize and shield that charge. So effectively, the charge you see is smaller than what it actually is. Because vacuum is kind of putting its tail, negative tail, positive tail towards it, negative out, and shields it. The same way like electrons now do not attract me is because the cloud of the atoms around them have the similar charge that shields them. Okay, so matter looks neutral. So, and if you get really close to an electron at 10 to the minus 11, you start seeing this divergence. Electrical charge is not really constant. It diverges. It gets larger and larger as you get closer to an electron. So it's by no means a fundamental constant. I mean, it's not clear. It could, in principle, be infinite. We don't know. No. And this is, and I want to emphasize, these are experimentally very successful, and they've been verified over and over and over. It's not some theoretical construction. It has really experimentally been verified. So, and this is a reference. So everything works well till 10 to the minus 16, 17. But if you keep pushing it, like this is how you understand nature, right? You have something that works, then you keep pushing it. You keep pushing it till it fails. Then when it fails, you're like, all right, so why did it fail? Maybe I need a new theory, right? So if you keep pushing this idea of probing space-time with more and more energy and momentum, more and more energy and momentum, at some point, like the so-called Planck scale, which is 10 to the minus 33 centimeters or 10 to the minus 43 seconds, can you read these seconds and centimeters from the back? Is it legible? Okay, good. So at these time scales, short time scales, you have to put so much energy into the vacuum that you make a black hole. To probe it, you have to put so much energy into it that you make a black hole. And when you make a black hole, like the name suggests, you can't study it. Nothing comes out of a black hole. Right? I mean, it doesn't radiate, it doesn't talk to you anymore. It's just a black hole. And then you're like, oh, what do I do now? So your physics, and if you say, all right, well, I can put more energy into it. Well, you just make a bigger black hole. Okay? So it just won't work. So it works all the way. Things work very well. Actually, they failed before the Planck scale. But at the Planck scale, it does not work. At Planck scale, the Planck time and length are, you see, 10 to the minus 44 and 10 to the minus 35. The so-called Planck mass is 10 to the minus 8 kilogram. And 10 to the minus 8 kilogram is not that small in comparison. You agree? I mean, you can actually measure it in a normal lab. So why do you think it's so large? It's funny, right? And 10 to the minus 44 and 10 to the minus 35 meters, these are really, really, really small. But 10 to the minus 8, I'm sure there are insects, like fruit fly maybe has this weight, right? So this is the mass of this black hole, okay? This says that this black hole, if its radius was 10 to the minus 35 meters, so its volume would be, the third power, say. So we're looking at 135, 10 to 135 minus 135. The density would be gigantic, right? You would have a density as mass over volume. Volume is 10 to the minus 35 comes on top, is 10 to the 135. Multiplied by 10 to the 8. The density is like, 10 to the 127, right? So it's huge. The density is huge. And that's what a black hole is, as gigantic density. Okay? That's why this mass is so large in comparison. So quantum mechanics has this uncertainty relation. Relativity has this equals mc squared, equivalence of mass and energy. This is just special relativity. You put them together, you get this vacuum. 10? Oh, great. You get this vacuum that's full of activity, okay? Full of flurry of activity. It's like a boiling soup of particles. You push it, you keep getting more energy. So the vacuum becomes even more and more energetic. And at some point, and this is at the distances far beyond the Planck scale. If you look at the energy density of the vacuum, right? This is before the theory fails, before everything goes crazy. You calculate this energy density and compare to the observation. So you see that this so-called lambda is this energy density of the space-time. It is so large that it's unbelievable. The calculation, the prediction of this standard model that's supposed to be so amazingly accurate in every sense just gives you a lambda that is gigantic. And that would imply, for example, that the universe doubles every 10 to the minus 43 seconds. It's that large. It's actually so large that people assert quite firmly and rightfully that it's the biggest error in the history of science. Not just physics. It's just 120 orders of magnitude discrepancy. In physics, we're used to getting things to 11 decimal places, and that's when we call it good theory. This is 120 orders of magnitude off. So what you measure is 1, and what you measure is 1, and what your theory says is that it's 1 with 120 zeros. It's that far off, okay? So then the question is, so what's going on, right? It's working so well, why is this working so badly? We don't know. But believe it or not, the way it's explained is by fine-tuning the argument. I'll tell you what fine-tuning is. It's ridiculous. So the only explanation we have now is that, okay, we don't know what it is, but what's happening is that there just happens to be another background density that cancels it to 120 decimal places. Do you see what I mean? So if I have a number that is very off from the other number, I just happen to have another one with a negative sign that cancels everything to 120 decimal places, and the 121st decimal place, they're different. And that's why the observation and prediction could match. There just happens to be this background density. Then you're like, well, what is that background density? They're like, well, it just happens to be there. Okay? That cancels things in exactly the right way that the difference would match this prediction value. Okay? Okay. Well, but I mean, right? This is crazy. So yeah, that happens to be there. But how can you explain it? Well, one way to explain it is the so-called anthropic principle, and that says the universe we have now. Now we're going to go back to large scales. So the universe we had. Now we're going to even look at space-time scales, humongously more than the scale of the universe. Scales that are just unimaginable, beyond the visible universe. And this is a depiction that the universe we live in, we have this Big Bang in our cosmology, but that's just like an atom in a bigger universe that has all these little Big Bangs and cosmologies. So each one of them has a different set of initial conditions and parameters, and therefore, they all could have different types of universes, different constants, different electrical charge. We happen to find ourselves in one that space-time is not growing so fast, and structure can emerge, life can emerge, and we just happen to be lucky to be in one. Most of these space-times, if you calculate, are empty and lethal. I mean, there would be nothing emerging in them. They're either expanding too fast, they're contracting too fast, they're too hot, they're too cold. Most of them are just deadly, lethal, and empty. But there's 10 to the 1,000 of them, say, and few of them, perhaps one of them, has just all the parameters right in such a way that we could have a universe like this. We could have trees, we could have Cortona week and so forth. Okay, and in that one, this fine-tuning happens because there's so many of them. In many of them, the fine-tuning doesn't happen, but in this particular one, it does happen. Therefore, we're lucky. Okay. So I could tell you more. How am I doing on time? But maybe I can. I have 5 minutes. Huh. Okay. All right. Okay, so I'm going to tell you about atomic clocks. So one thing quantum theory does very well is understanding atoms. The great thing about atoms, well, first, before, let me tell you what a clock is. So a clock is anything with some periodicity, right? Like these grandfather clocks, the way you measure time, you say, all right, I look at something as periodic, and I measure time against it. For example, I say this pendulum, when it goes back, forward, that's 1 second. I hang this in my wall, Reinhard has this in his wall, and then we can agree on time, right? So my 1 second would mean the same. So all clocks are based on periodicity. The oldest clocks we know are the sundial and the water clock. So sundial, again, is periodic based on the position of the sun. This is like the amount of time it takes for this jar to empty. This could be an agreement on time. You get the same clay maker to make those jars. You have one in your home, I have one in my home. We agree on, how many jar times we have to wait. Okay? But obviously there are problems. This wouldn't work at night, in cloudy days. This one works differently at different temperatures. It could freeze. And this hole, gets larger with time, so time is running faster. So, now we're going to skip some maybe 4,000 or 5,000, I don't know, 2,000 or 3,000 years of civilization and talk about atomic clocks. So there are watches and so forth, but they all work on some kind of periodicity. The great thing about atoms is that they don't change. A hydrogen atom is a hydrogen atom. If it changes, it becomes a different atom, right? So the great thing about atoms is that they don't change, their properties are invariant, and if you can use their fundamental frequencies, the way they oscillate, you can make clocks that do not change with time. Further, these oscillations are so fast, it's like your pendulum, instead of doing 1 second, it does like 10 to the 16 oscillations in 1 second. So you can hatch time with resolutions that are unbelievably fine, right? Because you can say, all right, 800 of these oscillations, and that is such a small fraction of 1 second that normally you would have, okay? So it's again periodicity, there's no different. Again periodicity, but just finer, more robust periodicity. Now how does it work? Well, this is an atom, say cesium atom, rubidium. This is an electron in its ground state. You need to provide this much energy for it to jump up. You start with a cavity that's close to this energy, and there's some error. when you excite it, it's a fact that this will only accept an energy exactly, a frequency exactly matching this for this transition to occur. So you see there are 3 waves here. 2 of them get through, but 1 of them excites it and this electron jumps up, you see? Now these go away, and there's a relaxation time, it falls back and gives out that photon again. Okay? Now you can grab this photon, put it into a feedback loop, and keep exciting it, and by this you can sharpen and sharpen and sharpen and sharpen that frequency, okay? So you get this monotone, I could show you, it might blow up the speaker, so I could show you what a feedback is. You see sometimes when the microphone makes this like a loud, that tone, that's a very monotonic tone. That's a very single frequency into a feedback loop, which, you either, if you want to keep it, you have to keep putting more energy into it, or actually your equipment will fail at some point. The amplitude gets so large that it blows up the speaker. Okay? So this is what's happening here, this feedback loop. And the reason it sounds so bad is because it's such a single frequency. Single frequencies don't sound good. In musical instruments, you want to have a wide range of frequencies for it to sound pleasant, various harmonies. Now, this monotone, when you make it very exactly, then you can, the technicality is the counter, and that will be the hatching of the time. Usually it's in a microwave regime, so you have, many oscillations per second. So the current state of atomic clocks is that the older ones lose a second every 100 million years, is how robust they are. Then the quantum clocks, the more recent one, 3.7 billion years you lose a second. So this is the hatching of the time I told you about. So every second can be cut into so many pieces. Okay. And recently there's been an advance that they can increase this accuracy by a factor of 2. So you can have 7.2 billion years and lose a second. All right. So with I think all right. So in the beginning we talked about the indefinite continuous progress of existence, right? The Oxford Dictionary, remember? And present, past, and future. We see that there's nothing indefinite about time, right? We have this Big Bang theory and the ultimate fate of the universe. There was nothing continued about it. At short scales, space-time fails. We don't even know what time means at very short scales, like far before the Planck scale even. And past, present, and future, with the time travel and everything, are very relative. And quantum theory also has some things to say about past, present, and future. So that also, regarded as a whole, is not very meaningful, this whole block universe picture. And then we talked about atomic clocks and frequencies and intervals. So perhaps Boltzmann's idea, let me just read it. Perhaps Boltzmann's idea can be restored that each of these big bangs corresponds to a fluctuation in a grand universe, that anthropic principle we're talking about, that is otherwise at equilibrium. So our world, including lives, dreams, and cosmology, are none but an ephemeral fluctuation sparkling the timeless existence. So with that, perhaps I can thank you. So I will just, thanks.
Thank you, Ramis, for a roller coaster ride from atoms to galaxies. Okay. It was awesome. So we have
different locations. So
Yes.
wouldn't it be more like a space-time travel, but not necessarily time travel in the same space?
That's absolutely true. It's a space-time travel. So in relativity, we don't distinguish space and time even. It is really so when you jump out of the one, you're where the location of the other black hole is, and perhaps at a different time. Yes.
Besides the potential for finding a solution to time travel, I'm just curious, going through all of this math and determining that, the 0.13 exponential thing is happening, what is your goal in researching this? Like, what do you see as the value of doing this research? Besides, God's equation, God yourself.
So I don't know. So what was the 0.123 that you talked about? That.
Well, you're saying, maybe there's a potential at 10 to the 1, 2, 3 that something happened at some point in time. And maybe someone else 50 years from now finds out that that's not true. Like
What's the value?
If you see anything but his wife's this whole life is basically,
Yeah.
there's no point.
So what's the point in fundamental research?
No. I'm just curious for you, what's your goal? What are you interested
My goal is the same as the fundamental research. I mean, understanding, well, one thing for sure is that this is not my research. So I'm talking about it. But I do admire people who do research it. I don't think it's a waste of time. I think the understanding the very fabric of space-time, like all these lab experiments you have, all the things that you do, the starting point is to have a space-time and interactions. And if way back before Newton, we had given up and said, what's the point of understanding mechanics when Newton was around, none of these labs would be around. So the possibilities offered by fundamental research are immense. And I think it's very worthwhile. And it's not easy, it doesn't necessarily pay very well, but people who do it, I think they do advance us as a whole. Perhaps not right now, but maybe in the future. It's at least one reason. There's aesthetics, there's the beauty of it, there's liking of it, passion, and so forth.
But so you're saying that maybe it's not possible to see the potentials of the results of the research right now, but at some point in time it opens up new avenues.
So that would depend really on the particular topic. But yeah, I mean, in the most pessimistic case, I think that would be the answer. But many of these, as I told you, they have been experimentally verified. And like we have quantum computers now because of, well, the possibility of quantum computation are very weak quantum computers because of such advances.
But when you're finding the Higgs boson particle, like besides making yourself feel like, oh, I was right, you know, my ego feels better. I'm just curious, like what?
No, it's not that. What Higgs boson says is that your picture of what physics was is correct.
We have time for one
yeah.
question.
Maybe that's something for the breakout groups, because it digs into more time. Am I right that space-time, as you explained it, and as is in the model, is just a side aspect of something which is much larger? Because before the Big Bang, there was no space-time, there was no time. So the question, what was before, is completely irrational.
That's right.
Yeah?
Yeah.
And if you come
If there
close
was
to
a Big Bang.
black hole also,
That's right.
it's not there anymore.
That's right.
So we would have to think in other terms.
Sure. So this so-called Planck scale physics I was telling you about is relevant at the Big Bang because of these high energy densities, but also at the small scales of, it's actually interesting. At these both ends it's relevant. And to go beyond the standard model, which you may hear often, to go beyond the standard model, those scales, we don't know what's the right way to go about it, but there are, propositions like string theory tries to do that. Tries to push into that understanding of, what happens beyond. But, there are not any experiments around it, and I have, mixed feelings about string theory, so I didn't talk much about it, and I don't know much about string theory to talk about. But yeah, I mean, at very short time scales and also in the very, very early universe, so 10 to the minus 43 seconds after the Big Bang, just earlier, the whole physics itself, the notion of space-time, because of that immense curvature, that smoothness breaks down. So the general relativity itself that predicts that start fails at that start. So yeah, we don't know how to go beyond it.
Would you allow me to give a very short, non-serious answer to the question before?
I would love to, yeah.
Because it also helps me.
Yeah, sounds good.
If respected people like physicists make theories which are wrong by a factor of 10 to the 120, it also helps other people making theories.
Okay.
Sure. Yeah, please do.
Yesterday I witnessed a discussion between and I just really needed.
No, go for it. Yeah.
Yesterday I heard a conversation between Reinhard and Brother David, and during the discussion, Reinhard was basically questioning the Big Bang theory. I really want your take on this. What if this theory is not accurate, the Big Bang theory?
So you're asking the right person. So I actually, back when I was in Reinhardt's group, the good thing was that, you could do a lot of crazy things if you wanted. And I did make a serious effort trying to find a counter picture for the cosmos. So, in principle, there are a few. One is the redshift. There are a lot of experimental data. So what I presented to you is what physics believes to be the case, not my opinion necessarily, okay? But we have to be honest to ourselves. It seems like all the experiments are pointing to a Big Bang theory. Now, if one wants to bring down the Big Bang Theory, you have to put in a lot of work. So there is the redshift that I think we can explain. There's an alternative way of explaining the redshift. But there's a lot more. There's the cosmological microwave background radiation that may be explainable, but then there's the atomic distribution in the universe and all sorts of things that together seem to confirm. If you connect the dots, you get this Big Bang Theory. Now, actually the term Big Bang, it sounds ridiculous, right? I mean, for a cosmological term. And it was meant to be a mockery. Fred Hoyle, after he saw that the solutions all pointed out to a single start, you should imagine at the time everybody thought the universe was infinite, right? So they said, yeah, as if it started from a Big Bang. So that was supposed to be a joke, but then they saw that as time went on, this joke persisted and the term Big Bang stuck. So to go beyond it, as I said, there's a lot of experimental things you gotta theoretically explain in a simpler way than what's already in place.
I apologize, Ramis.
The implication would be a new cosmology, new space-time, new understanding of space-time. I don't think that'll disprove general relativity or quantum mechanics, but the cosmological origins of where space-time come from would have to reorganize.
We are running out of time. Maybe we can continue discussion in the break. Yeah. Thank you very much to Ramis.
Yeah, you're welcome. Thank you.